The aurora, often described as one of nature's most magical light shows, has intrigued and captivated people for centuries. These shimmering lights, most commonly observed in the polar regions, paint the sky with vivid greens, reds, purples, and blues. But what is the science behind the aurora? How do these beautiful lights form, and what makes them so special? The story of the aurora begins with the sun. The sun is constantly emitting a stream of charged particles known as solar wind. These particles, made up of electrons and protons, travel through space at incredible speeds, sometimes reaching up to 1.6 million kilometers per hour. The solar wind carries energy that reaches Earth, and it is here that it interacts with our planet's magnetic field and atmosphere, giving rise to the aurora. Without the solar wind, we would never see the stunning light displays that have become so closely associated with the polar regions. As the solar wind travels toward Earth, the particles are deflected by Earth's magnetic field, which acts as an invisible shield around the planet. The magnetic field is strongest near the poles, and this is why auroras are most commonly seen at high latitudes. The magnetic field guides the charged particles toward the poles where they enter the atmosphere. Once the particles reach Earth's atmosphere, they collide with gases such as oxygen and nitrogen, which causes these gases to release energy in the form of light. It is these light emissions that we perceive as the aurora. The colors of the aurora, one of its most mesmerizing aspects, are determined by the gases in the atmosphere and the height at which the solar wind particles collide with these gases. When the charged particles from the solar wind interact with the atoms and molecules in Earth's atmosphere, they excite them, causing the atoms to release energy. This release of energy results in the production of light, which is why auroras are so vividly colored. The most common color seen in auroras is green. This color is produced when solar wind particles collide with oxygen molecules located about 100 kilometers above Earth's surface. When these oxygen molecules are excited, they release green light. Red auroras, on the other hand, are caused by the same type of oxygen molecules, but at a higher altitude, about 320 kilometers above the Earth's surface. At these higher altitudes, oxygen molecules emit red light when they are excited by solar wind particles. In addition to green and red, auroras can also produce shades of purple, blue, and yellow. Purple and blue lights are generated by nitrogen molecules, which exist at lower altitudes in the atmosphere. When nitrogen is excited by solar wind particles, it emits blue or purple light. Yellow, a less common color, can appear when both red and green lights mix together. While the solar wind and the atmosphere play crucial roles in the formation of auroras, Earth's magnetic field is equally important. The magnetic field acts as a guide, directing the charged particles toward the poles, where they are most likely to interact with the atmosphere. Without the magnetic field, these particles would not be concentrated in the areas where auroras are most commonly observed. The magnetic field is not uniform across the planet. Its strength varies, and it is most intense near the poles. This is why auroras are most frequently seen in high-latitude regions such as Alaska, Norway, and Canada in the northern hemisphere, and Antarctica in the southern hemisphere. The charged particles follow the curved lines of the magnetic field, which is why auroras tend to form in arc-like patterns that are shaped by these lines. The aurora often appears as a band or arc across the sky, and in some cases it can form complex swirling shapes. While auroras can occur at any time, their intensity varies depending on solar activity. Solar storms, also known as coronal mass ejections or CMEs, are major bursts of solar wind and magnetic fields from the sun. These storms send large amounts of charged particles toward Earth and can significantly enhance the aurora's intensity. During a solar storm, the solar wind particles are more energetic, which means they interact more forcefully with Earth's atmosphere. This leads to brighter and more vivid auroras. In some cases, solar storms can cause auroras to be visible at latitudes far from the poles. People living in regions such as the northern United States or parts of Europe have reported seeing auroras during strong solar storms, even though these areas are far from the polar regions where auroras are typically seen. Solar storms also provide an opportunity for scientists to study space weather, the term used to describe the interaction between the solar wind, the magnetic field, and the atmosphere. Understanding space weather is important because it can affect satellite communications, GPS systems, and even power grids on Earth. Auroras do not form at random locations on Earth. They are typically seen within an area known as the aurora oval, a region around the magnetic poles where the Earth's magnetic field is strongest. In the northern hemisphere, the aurora oval is centered around the magnetic North Pole, and in the southern hemisphere, it is centered around the magnetic South Pole. The aurora oval is not a fixed region. It changes size and location depending on the level of solar activity. During times of high solar activity, the aurora oval expands, making auroras visible at lower latitudes than usual. This means that in some cases, people in areas like the northern United States or even the United Kingdom may be able to see the aurora during a period of intense solar activity. In fact, the aurora oval is the reason why auroras are most commonly seen in countries like Canada, Norway, and Finland, as they lie within the aurora oval. To witness an aurora, one must be in the right location and at the right time. The best locations to view auroras are at high latitudes near the poles. The best time to see an aurora is during the winter months when the nights are longest and the skies are darkest. For example, in the northern hemisphere, auroras are most commonly seen from late fall to early spring, with peak viewing times around the equinoxes in March and September. The strength of the aurora is also influenced by the solar cycle. The sun goes through an 11-year cycle of activity, with periods of high solar activity, or solar maximum, followed by periods of low solar activity, or solar minimum. During solar maximum, the likelihood of observing a strong aurora increases as the solar wind is more intense and produces more energetic particles. The aurora is a captivating natural phenomenon that results from the interaction between solar wind, Earth's magnetic field, and the atmosphere. It is a reminder of the power and beauty of the forces that shape our planet and the universe. The aurora's formation is a complex process, but its stunning display of light and color is a direct result of the sun's energy, Earth's protective magnetic field, and the atmospheric gases that surround us. The aurora continues to inspire wonder and awe, and it serves as a powerful symbol of the connection between Earth and the vast cosmos. As we continue to learn more about the science behind auroras, we gain a greater understanding of the intricate forces that shape the natural world and the universe beyond.